Okay, today's lesson is going over chapter, or the first section in chapter 3, 3.1. It's basically an introduction to quadratic functions, the shape of their graph, their key features, and other things like that. So we're going to go through this and see if we can talk about identifying and describing. Really the goal is to write the key features of a graph and understand what they are correctly. So if it's a point, we want to make sure that we use point notation. If it's a line, that we use linear notation. Intervals, the correct interval notation. So we just want to make sure that that's what we're looking at. And essentially when we talk about key features of a graph, right, what we're talking about is the behavior of the graph and its relationship here. So for example, this would be, it's kind of easier to see on an application maybe. But if I were to ask you, like, what is the domain of this particular graph right here? This is comparing, right, degrees in Fahrenheit over time. If you're looking at the domain of what this graph even shows, right, it only shows the hours from 9 a.m. until 9 p.m. It doesn't tell you anything about midnight or 1 a.m. So our domain is very restricted on this one. Our range, right, if we were looking at key feature range, we would say, well, the lowest this ever goes is 72, and the highest it ever goes is 88. So our range here is from anywhere from 72 to 88 degrees. It always stays within that. And then you'll notice there's different sections on here that are increasing and decreasing. And graphs are always moving left to right. So I wouldn't say that, I would say, well, the function has an increasing or a positive slope from 9 a.m. to 11 a.m. We would never say from 11 a.m. to 9 a.m. Going back in time. So we're always moving in a positive direction, left to right. And you'll notice, right, there's increasing pieces, there could be decreasing pieces. The temperature is definitely changing, but we would talk about using this time or this x-axis to describe when they're increasing or decreasing. So notice from noon until about 3, the temperature is increasing, right? So these are all key features. These are all things that we're going to look at. Maximums and minimums. Notice this is the maximum temperature, right, of 88 degrees, or there might be a minimum temperature here. So as we move forward through these parabolas, I just want you to kind of think about the key features. Do they represent a point, a line, and how would I write that correctly? So we're going to talk specifically about quadratic functions. Now remember, quadratics were any function or expression, right, that had a degree of 2. Degree of 2, remember, degree means the highest exponent. So some examples of that would be like 2x squared plus 5. That exponent right there is the biggest exponent. It's the only exponent, and it is a 2. It could also be something like negative 10x squared plus 3x plus 15. That's also, right, that's a trinomial, but its highest degree or its highest exponent is 2. If we look at something that's just like negative 4x squared, that also is a monomial with the highest degree of 2. You could also write it in factored form. So let's say we had a factored one here, x plus 7 and x minus 10. That's also a quadratic. It's just factored form. So anytime we have a degree of 2, we are talking about a quadratic function. And anytime you draw or graph a quadratic function, it creates a U-shape. We call this U-shape a parabola. Okay, now the U-shape can either open up, in which case it looks like it's smiling, or it can open down, in which case it looks like it's frowning. Okay, their behavior very similar to what we'll see with transformations in an absolute value function. But they do differ, right? If I shoot this bird and I want it to land over here to the right, because of gravity, what goes up must come down. So in this case, if I launch this bird, if I were to try and launch it in an absolute value or a V direction, it would have to hit something that would ricochet it or reflect it to make it come back down, right? In reality, I would launch this and it would make more of a parabolic shape, so more of an arch, and then it would come back down. At some point, it would hit a maximum height up here. Just like our V's, we call that a vertex, right? That maximum point at which it changes from an increasing to a decreasing. And again, that's the highest point that bird ever reached. So we would call that a maximum vertex, or that vertex a maximum. Notice it's increasing in height for a little while. So we would call this an increasing on the left side before the bird starts to decrease in height. I guess I should write decreasing because I wrote ing. Those are two key features that we're going to focus on today. So an increasing and a decreasing interval. They also, have our x-intercepts. We were pretty good at those. So this x-intercept is at 0, 0. And let's put some tick marks on here and call this 4, 0 on the right. Let's draw some 1, 2, 3. So for a certain amount of time, our bird is increasing in height, then starts to decrease in height. Parabolas are always symmetric as well, so we have this invisible line that goes right down the middle that we call this axis of symmetry. The axis of symmetry is the line that cuts the parabola into two symmetric halves. And we always write it as a line, right? It's a line that we could fold the paper on and it would cut it in half. This is at x equals 2. So notice there, that line right there would be like cutting it into two symmetric halves. On one side it's increasing, the other side it's decreasing. So those are some of the new features that we're going to look at. And again, any application where we have an object going up and coming down, we're going to practice writing it with a parabola or a quadratic function. So let's look at the parent function. I guess this asks us to identify other activities or actions. Hopefully you can think of a few, right? Any sports, throwing a ball, anything that's done over time that increases and then decreases at that parabolic rate. Architectural structures, so you can think about like the McDonald's M, you could think about the St. Louis Arch, anything, the bridges, right, that are held, suspension bridges that are held up in that way, those would be parabolic arches. So we see them a lot, and we're going to do some applications once we've practiced with these functions. So let's talk about the parent function. Remember, before we dove into anything related to our absolute value, we also looked at the parent function. So I just want you to kind of remember the parent function for absolute value looked like this, right? It was the absolute value of x, and anything we did to that and to change it was a transformation. When we drew its graph, it sat at the origin and it had a slope of 1 unless it had been transformed. The parent function for a quadratic is y is equal to x squared. Any change made after that is a transformation on the parent function. And we want to plot some points to kind of determine what this function looks like. So let's look at its behavior. If I were to take this -4, let's say I plug in a -4, and you could put this whole thing into a calculator and get a table that way. But if I plug in these values, so -4 squared is just -4 times -4, that's a positive 16. -3 times -3, positive 9. -2, right, squared is a positive 4. -1 squared is just 1. 0 squared is 0. And then moving into my positive values, if I put a positive 1 in, that's 1. 2 squared is 4. 3 squared is 9. 16 squared, 4 squared is 16. And 5 squared is 25. So if we come over here and plot these points, right, every value here represents an ordered pair on the graph. I would go -4 up 16, and that would be a point on my function. -3 up 9, again a point on the function. -2 up 4, a point on the function. And we can just plot these points, and then notice if we keep plotting them, right, it creates two symmetric halves. That last point, 525, goes off the graph, so I just wouldn't draw that one. And then you do the best you can to graph these with a U shape. So this is not an absolute value function. Notice it's not linear. So a lot of the functions you've done up until this point have been linear in behavior. This one's changing at a rate of perfect squares. So here it's like over 1 up 1, right? Because 1 squared is 1. This one's over 2. 2 squared is 4. So notice it went up like the 4 units. Over 3, it goes up 9 units. So we can tell that this is going up 1, 4, 9, 16. They're going up by perfect squares. So that rate is definitely increasing as we go. So if we're going to identify the vertex on this one, again, this is just for our parent function. It hasn't left the origin, so it's still sitting at the origin. Because this is a low point on the graph, so it's the lowest point on the whole graph, that vertex, we would call that point a minimum. Our x-intercepts, notice there, haven't moved from 0, 0. So very common with a parent function. And the domain, right? Notice there's arrows going in both directions on this. So the domain on this is a lot like an absolute value. There's no holes in our graph. We're going to have negative infinity to infinity. Or for those of you that like to write all real numbers, that's fine too. The range, again, like an absolute value function, never drops below this value, or this like line here, right? That's like an invisible line there. It never comes down here. So our range is anywhere from 0 up to infinity. That works for our graph. Oh, that's a 0. And we use a bracket on there. Or again, for those of you that like to write y is greater than or equal to 0. The axis of symmetry, if I were to fold this parabola in half, it folds right on that y-axis, or in other words, where x is 0. So again, we write it as a line, x is equal to 0. And then increasing and decreasing, this is the one that's a little bit different, but notice there's always two pieces to this, right? There's an increasing and a decreasing. So here's our axis of symmetry. If I draw a little hiker on here, you'll notice that the values, we always read them left to right, the graphs. They're decreasing to start with. So again, if these were representing like temperatures, we're going down in temperature first. Then we start to go up. So when we talk about where is it increasing or decreasing, well, it's decreasing from negative infinity until we hit that axis of symmetry. That axis of symmetry then is kind of that cutoff point, and then we start to go up and we increase until infinity. So that 0, there's two intervals there, right? We're decreasing first, then we start to increase. So as I write my intervals, my decreasing, right, was from negative infinity to 0. It was on the left side of the graph, and then we started to increase from 0 to positive infinity. If you want to use inequality notation, you could say, well, decrease is on the left, so I use this, right, points left of 0, and it increases on the right, or in other words, that's points greater than 0, so you can use that as well. Okay, so let's practice just a few of these at a time, and then we'll kind of grow on it. So I would almost pause the video right here if you're working on this for the first time, and try these out, and then come back and check your answers. I'm going to work through them rather quickly. The first one is just the parent function. So that axis of symmetry is there still at x equals 0. That vertex hasn't moved away from the origin, so it's still sitting at 0, 0. And that vertex represents the lowest point on the graph, so we would call that a minimum value. The next one, axis of symmetry now, is over here. It looks like at 4, so x is equal to 4. The vertex then is at 4, 0. And that point is a low point, again, on that parabola, so it represents a minimum value. Graph number 3, axis of symmetry. Here at x equals negative 1. Your vertex there is the point negative 1 down 2, so negative 1, negative 2. And again, that's a low point on the graph, so it would be a minimum. Graph number 4, axis of symmetry, again, is over here. This one's flipped upside down, but it still just has that axis of symmetry at x equals negative 3. Our vertex here is negative 3, or over 3, right, up 5, so we're at negative 3, 5. And that's the highest point on the parabola, that vertex, so that would be a maximum point. Number 5, again, your axis of symmetry there, x equals positive 1. Your vertex right there at the top of your parabola is at positive 1 and up 3. And again, it's at the top of the parabola, so it represents the maximum height on your parabola. Graph number 6. So this is an absolute value function, but I just wanted to show you that it does the same thing, right? Notice there's an axis of symmetry here. We just didn't talk about it yet. X is equal to 3. There's also a vertex, so that one we did talk about. So it's at 3, negative 2. And that is the lowest point on your absolute value function, so it represents a minimum. So this really isn't any different than what we've seen. These are just going to be U-shaped graphs. Different rates of change. What relationship exists between the vertex of the graph and its axis of symmetry? You'll notice here that the axis of symmetry is always the x value of the vertex. Because it's cutting it in half and the vertex represents that point where it changes, it's always going to pass through that vertex. So we can find that pretty quickly from vertex form and other things. Again, if I want to find the axis of symmetry, I just need to know where the vertex is. because it's always x is equal to, and then this is the x value of the vertex. Okay. Just a reminder with increasing and decreasing. So unlike linear graphs, which is always increasing or always decreasing, a parabola represents a function that has an increasing and a decreasing half. So if it goes up, it has to come down to create that U shape. If it goes down, it has to come up. So how do we know which is which? Remember, we always read in graphs and define intervals left to right. So if Henry's going to hike on the function from left to right, he's going uphill first. Now there is an arrow headed the other direction, so you need to recognize we're moving left to right. So he comes from this side and he's going uphill. If the graph is going down here, we know that's a negative slope. He's going downhill, or the values are decreasing as we move to the right. So we are either increasing, in which case it looks like those values are going up, or we are decreasing. Okay. So let's try this on a couple of these. The first one, again, if I'm going to identify the vertex here, the vertex is going to be at 0, -1. So it's that low point, and because it's a low point, we call that vertex a minimum. The axis of symmetry, if I were to fold this graph in half, it would fold right there on the y-axis. So that axis of symmetry is also x equals 0. And then the roots, or x-intercepts, we can practice writing those as well. They're just where the graph crosses or touches the x-axis. So there would be two of them on here. It's crossing at -1, 0, and a +1, 0. Remember, those represent solutions on the graph. And then increasing and decreasing. So remember the function, here's my axis of symmetry, has two pieces. There's the left side and there's the right side, and it's going to increase or decrease on either side of that axis of symmetry. It looks like this guy would be hiking downhill, So from -∞, he's going to hike downhill until that axis of symmetry. Then he's going to start to hike uphill till infinity. So decreasing comes from -∞ up to 0 or over to 0. And then it starts to increase on the right-hand side. Our domain there is -∞ to infinity, and notice the range, the graph never drops below -1. So from -1, that's an infinity. From -1, the graph just goes up forever. Okay. The next one, the vertex here is 4, +2. So we're going to write that as a point. That's the high point on the graph, so that is a maximum. The axis of symmetry, again, is this line that cuts it in half. So we're looking at x is equal to a +4 there. Again, that 4 should match the x value of your vertex, so it looks good. Our roots, or our x-intercepts, where it's crossing the x-axis, would be here at 2 and here at 6. So we write those as points, the point 2, 0 and the point 6, 0. Again, if you look at this graph, there's my axis of symmetry. Notice if Henry's standing on here, he's actually hiking uphill first. So this time from -∞ until 4, we are increasing. Then we start to decrease. And notice it looks like, that's headed to -∞. But remember, we're not talking about y values. We're talking x values, and they're getting bigger and bigger. So it decreases from 0 over here to +∞. So increases first, he hikes uphill, not to 0, to 4. Then he hikes downhill from 4 to infinity. Our domain stays the same, -∞ to infinity, and our range there is coming from the bottom. So we're looking at -∞ all the way up to a +2. The +2, is where our graph sort of caps, right there. Okay, let's talk about really quick the behavior and the transformations. So when we look at these, we're looking at basically kind of what we looked at with the absolute value function. So I want you to notice that this is very similar to the absolute value function. If we change this a value out front, remember it stretched or shrunk. If we added something on the end, it went up or down. If we put a negative out front, it flipped it over. And the same thing is true here. If it's a -a, then it has been reflected over the x-axis. and that means that it's going to be opening down. So a quadratic function opens up all the time unless there's a negative out front. If that a value, right, was greater than 1, that was a vertical stretch. So we know that it's going to get super tall and skinny. And if a is between 0 and 1, so it's like a fractional value, then that was a vertical shrink. And it shrunk the slope, or the rate of change, so that it was much wider, where a stretch made it really tall and skinny. And these ones get super tall super fast. So we just want to be aware of that. And then adding a value on the end, again, this shifts it up or down. So just like an absolute value function, we're looking at that. Notice your functions today, I'm going to show you with this h of x, doesn't have that middle term. So we're just talking about if it had a value on the end here and maybe a reflection and a stretch or a shrink here. So graphing this function right here, I'm going to talk about this on the next video, just for the sake of time. The bell is going to ring. So I will end this video and pick up just this very last part of these notes on the next one.